Welcome back, my structural analysis friends. In this lesson, we're going to be looking at some basic statics review, because after all, you can't do structural analysis if you don't know statics. So this will not be a thorough development of the statics equations, but more just a couple of sample type examples just to help kind of knock the rust off, so to say. So without further ado, let's get started. Alright, so as expected, the first step in solving any statics problem is always drawing a free body diagram. So we're going to go real quickly and review the basic requirements for those. This acronym came up, was one of my students actually came up with this, and it's actually very creative, so I'm going to borrow it, so to say. And the idea is that it's always wise to draw a free body diagram. All right, and so what we came up with was that W should stand for the weight, which is like the self-weight of the member. Different than a dead load, but the self-weight of the member. This is often neglected in most statics problems because often you don't have the sizes, or it's just not done in a preliminary analysis. In a final analysis, you have to include everything, so make sure we include it. But in problems in statics or in this class, generally you know that you have a weight that needs to be included if you see some mention of the mass of the object. Now, if it's an SI units problem, it's measured in kilograms. If it's or it says something specifically that the object weighs, 100 pounds or whatever. So you will know that you have this. But if it's not expressly written in this class, then we won't be dealing with it at all. Okay. That being said, we do consider like the dead load of a concrete slab. That is technically the weight. So we do kind of include some of the bigger quantities, but just. But yeah. All right. The second one, I, is for internal forces. And so I've got a couple of diagrams for this. These are forces that develop as a result of equilibrium. Okay. So imagine, I have a tension member in which I'm pulling on the end of it with a force T, both of it, and I decide to cut in the middle. Well, if I cut this guy in the middle and then I hide that, you can see that this object clearly is not in equilibrium. So this guy develops as a result of the cut, and it will always form on a cut line. Okay, in order to balance the external load. So these T's are externals, and then this T internal develops when I cut to look inside. So that's kind of what we say when this member has tension all throughout it, that no matter where I cut it, the picture looks exactly the same. And likewise, if I look at the other side of it and I cut, then I get a T in the opposite direction. So these internal forces can actually act both directions, depending on which side of the line that you're acting on. And that can be a cause for some, some trip ups and some confusion sometimes as you're working on these for the first time. But at this point, I think we're pretty good on that. Same thing for beams. Okay, so I've got a beam with a point load, with a pin reaction with AX and AY and a roller reaction with BY. And I decide to cut this beam, say here arbitrarily at some location. I called it as X. Okay. And if we go and we draw the free body diagram of this cut, then you can see that if I don't include the stuff at the cut location, clearly this object is not in equilibrium, especially with a length. This thing could rotate or do any number of things relative to it. So these three effects, the shear, the moment, and the normal, all develop as a result of those. Now, one thing to point out is that this, I've assumed what we call a positive sign convention for the beam, and we'll talk about that a little bit more here in a second, okay, in which, to the right is positive for the normal, counterclockwise positive for the moment, but the shear is positive down when you're on the left or to the right of the cut. So this dotted line again is that cut line. So anything that's acting on the right side of that cut, this guy is down. Whereas if I go to the other side and my cut line is now this dotted line, everything flips, because again, just like what we had up here where these internal forces had to balance each other at the cut, so do they have to balance each other on a beam as well, or a frame, or any object. And so everything that's here is opposite here. So now shear is up, in is to the left, and the moment is now clockwise on those. So that's a kind of part of the way that we set these up. So that's our internals. Okay, our support reactions, and we'll come back around to sign convention in a second. Okay, our support reactions we can show on this page. Set ourselves up with the awesome yellow paper now. Okay, the majority of the supports that we have, the three basics that we'll deal with in this class are roller, pin, and fixed. Okay, for a roller reaction, it's a single vertical. This guy is oriented such that it's perpendicular to the support surface. So if you have a support surface here with a roller on it, then your reaction has to be perpendicular. It has to turn also. So that's the orientation of a roller. Okay, so if you can just remember that orientation, you should be in business. Pin, I need to have two forces. Normally we assume horizontal and vertical, but that doesn't really matter so long as, if this is my force set, as long as they're as a pair oriented, that I have, two that are not in the same direction, I can define that, because what we're really after is the resultant of these. But normally we just call it Rx horizontal, Ry vertical, and we go from there. Okay, and then the fixed support, the situation is I have the same two horizontal verticals. Again, they could be in any orientation, and then I have a moment in this case, and I went and chose to go to, again, counterclockwise positive when I drew this on here, and I'll show you why here in just a second. That I'm always consistent to the directions that I draw things when I don't know what their true direction is. Okay, and so now boundary conditions that exist for these support types. If I go back up to the roller, you know that a roller is basically something sitting on a wheel or a bearing or something. It's free to rotate, and so this thing, there's some angle that we have as orientation of theta associated with that. And just like over here, this guy, if he's pinned, he's free to rotate, and so there's a theta that can live there as well. This guy, the fixed, theta boundary condition is 0 degrees. Okay, that it doesn't. That before anything changes, it comes straight out of the wall perpendicular, and then it starts to deform under the load. Okay, so it's a restraint due to the moment. Now, one thing that you'll notice is that basically these support conditions are restraints of motion. Okay, notice that up here, this is like saying, for the roller, that M is equal to 0, and then Rx is equal to 0. Okay, because it's free to rotate, and also because it's on a wheel or a roller, it's free to move to the left or right, or move in the x direction. So because it's free to do that, these two values have to be 0. Okay, whereas Ry is restrained, in this case in the vertical direction. So what's really happening is that at this location, delta y is 0, the displacement is 0, which induces that force. You have to have this force to hold the object in place. Okay, and so if you can remember these boundary conditions, there's this play on deformation versus the actual support reactions as we look at them. Come down and play the same thing here. Delta x is 0, delta y is 0. That's one of our boundary conditions. Okay, but here the other one is that the moment is 0. Okay, because theta is not 0. So what happens is that either a force is 0 or its behavior is 0. Okay, and so that's what we're looking at. So here theta is not 0, so the moment has to be one or the other is. And so these 6 items together will form the heart of some of the boundary conditions that we'll look at when we get later on in the class and start actually applying some of the mathematics to these principles. For basic statics review, that's kind of getting ahead of ourselves, but at the same time, this is a structural analysis sequence. We want to explain things a little bit more in a little bit more detail. Okay, and then likewise, we play the same game down here. Now I have all 3, so here theta is 0, delta x is 0, and even delta y is 0 on that. Okay, because it's not free to move up, left, or rotate as a result of that. Okay, so that's what we have happening there. Okay, the last item on our list then, okay, if we come back to our basic list, was the external loads. And those are pretty obvious. Those are the point loads or the distributed loads or the applied moments that are acting on the structure themselves. So you'll always know what those are, or you'll be calculating. In the case of the loads that we've been calculating with wind and snow, those are all externals. Okay, so that's the nature, and these 4 things constitute what we need to know about our basic free body diagrams. Okay, now let's talk a little bit about sign conventions. There are several sign conventions that run through structural analysis. Okay, the first one is the one that you probably learned back in statics. It's called the right-hand rule, and it's basically that x positive is to the right, y positive is to the left, and then the rotation moment counterclockwise is positive. If you remember, it's kind of if I can get my hand under here, it's the old right-hand rule that the thumb is x, the forefinger is y, and then the finger that's sticking up perpendicular is the rotational axis. And if you remember that there are lots of right-hand rules that came out of statics, this follows that sign convention. So these two match the right hand. This is my right hand. Okay, and then this one that is acting up, if I show this as the axis in the direction of that middle finger, the right-hand rule wraps around this direction with my thumb pointing toward the positive end on this. I know this is really confusing if you haven't seen it before, but if you notice that direction of my hand curling matches the direction of this arrow, that's the right-hand rule. It's actually two right-hand rules put together. And so a lot of the vector calculations that you did back in statics required that in order for certain operations where the cross product has to be a right-hand rule set to be able for the cross product to give you the right signs on rotational effects such as moments and those kind of things. Okay, now I say that there is one other convention that kind of came in statics and mechanics materials and will show up again in this one, and that's what we call the beam diagram convention. Okay, so I'm going to show you real quickly kind of what that is. It kind of goes back to our idea of cutting and exposing stuff. An axial force is considered positive if it pulls on the cut. So if I'm to the left of the line, it's pulling on the line. If I'm to the right of the line, it's pulling when it's to the right. Okay, that's considered as a positive axial load case. Okay, for shear, here's my cut, and now it's this way. If I'm to the left of the line, it forces the left side up. If I'm to the right of the line, it forces the right side up. So if you can remember, just draw the cut line whenever you cut a structure, and then look at these diagrams, and this will get you the sign convention that you need. It's important for the moment diagrams. Now, the moment's a little bit more odd, and I'm going to give credit to Dr. Cohen, my statics teacher, 30 years ago on this, that to this day, this still sticks with me, that she showed us this as a way to remember, and it just made all the sense in the world, so I'm going to show it to you. Okay, I'm going to put moments on this direction, okay, and this will match what we did in the last one. So if I'm to the left of the cut, putting a moment on, it goes clockwise. If I'm to the right of the cut, it goes counterclockwise. And the way that we remember these directions, because that's what we want, what we're after, I'll call that as positive, okay? And if I were to allow this beam to deform, and even though it's statics and deformation isn't possible, in reality it would cause that beam to want to kind of bow down because I'm kind of taking it and I'm bending it that way, right? Okay, so if I call that as some teeth, okay, and I put a couple of eyeballs on this thing, okay, the saying that she said that stuck with me all these years later is that positive moments make us happy. Cheesy little picture, I know. Dr. Cohen, I love you for this because it makes sense. So anyway, that's how I remember the direction of the moments, is that positive moments make us happy and cause this thing to want to bend down. Okay, anyway, yeah, so that's your corny pun of the day right there. Okay, all right, so let's get on to some of the other aspects of it. So for the rest of this video, we're going to kind of walk through some seemingly simple examples, but just kind of, again, getting our feet wet and getting reacclimated to some basic statics principles. The problems will be a little bit more complex than what you saw maybe in certain parts of structural analysis and statics and things that we've done to date, but that's kind of my intent. So I'll kind of walk us through some of these problems that I have set up for us. Okay, so if I take a look at this, what I have is I have a beam that has a roller support here. It's kind of hard to see. It's okay. Has a roller support there, and then we have a pin support here, ABC. I have a point load of 12 kips at an angle of 60 degrees. Okay, get some really weird light correction going on here. Sorry, I apologize for that. The yellow pages do that sometimes. 10 feet to the point load, 10 feet to B, and then I have a cantilever on the end with a point load of 6 kips acting at 5 feet. And 6 kips is acting down, and then the angle of the slope is at 3 rise, 4 run. Okay, it kind of gives you the angle, if you will. Okay, and what we want to find then is the reaction at A, and then the reactions at B. In this case, we're going to assume BX and BY. So the first step that we want to do, our solution process, is we've got to draw the free body diagram. Okay, and so if we look at this, okay, the only thing I did leave off, I left off a 10-foot dimension here, that's a 10-foot dimension there, and that's a 5-foot dimension there. Okay, that the free body diagram for that picture would look, if we go through our Y's, there is no weight, there are no internals because I cut nothing. So the first free body diagram that you draw, cut nothing. So that gets rid of the I. So this is just an SE problem. So support reactions, I have a pin support at B, so that's BY and BX. And then I have this roller, and we said that a roller, since my surface for my roller is actually at that angle 345, then in order for this guy to be perpendicular, he has to be oriented such that it's 3/4 up. And that ensures a 90-degree angle for proportions. Okay, so that might be a little bit tricky, so just make sure that you understand that part as well as we look. Okay, and then I know that this is 60 degrees there. Okay, and with that, now we have everything we need to be able to jump in and do statics. So the basic equations for statics, as you remember, are forces X equals 0, forces Y equals 0, moments equal 0. So that's our basics. We always come back to this. This class is no different. Sir Isaac Newton gave us those equations, and they knighted him for a reason, so he must have been doing something right, is the way I always saw it. So if that's the case, we'll go through and we'll plug in. And so we'll start off with the forces X, forces Y. And so if I take this equation, I can see that the X component of RA is 3/5 of RA. Okay, and I generally draw these so that I assume a direction, and I'm going to assume the right-hand convention almost always on this. So 3/5 RA, his component would be horizontal. That's why it's a positive here. Okay, and then minus 12 times the cosine of 60 degrees is the X component of this guy. His horizontal component is to the left. That's why he's negative. And then plus BX all equal to 0. So that's one equation. Now I can't solve it because I got two unknowns happening here. Okay. For Fy, we do the same thing. Now it's 4/5 of RA acting up. I'm not sure why I have a 20 on there. Oops. That's a little odd. Okay, because we're not doing a moment. Okay, so it's just 4/5 of RA. Okay, and then minus 12 times the sine of 60 degrees plus BY. And then minus, I pick up the 6 kips that's acting out here because he's in the vertical direction also. Okay, so that gets us to 0. Okay, and then, again, we have two unknowns. So normally it's the moment equation that helps us to unlock these things. And one of the things that I'll do with a moment equation is if I have a setup that's like this, generally I try to choose to sum a moment somewhere where my most complex load case is. So I could choose to sum it at A or sum it at B. Normally if I have a pin support, I sum it at the pin support. Okay, because if I do that, then BX and BY will not show up in that equation because their distance is 0. So then all I have to do is deal with this one guy over here. Now, he may have an extra Y component because he's at an angle, but that's another matter altogether. So what I chose to do is I sum moments at B. Again, there's multiple ways to do this. This is just the way I chose to do it. Okay, and so then we do our MB. This should be minus 4/5 of RA, and that's where the 20 should have been. Okay, I wrote it on the, apparently I missed it on the last one. Okay, so times minus 4/5 of RA. So that's the vertical component of him times 20. There is no X component because if you look at the picture, the X component actually acts through the point. So that's why there would be a 3/5 of RA times 0. So I didn't write that term in there. Okay, and then I have 12 times the sine of 60 is the vertical component of this guy. Whoops, pull it down here a little bit. Okay, it gets me that times its distance of 10, and then the cosine 60 term on the horizontal is also acting through that point, so that's why it's not there. Okay, now the directions these are making, so my RY is causing me to go clockwise, that's why it's a negative, and my 12 sine 60 is causing it to go counterclockwise, that's why it's a positive. Okay, and then this 6 guy is 6 times 5, and he's going clockwise, that's why he's a negative. And with that, now I have everything I need to be able to solve for RA. Okay, so RA is actually 4.62 kips acting at the angle that's indicated. Okay, all right. So once I have RA, then I can go back up to these two equations I derived from forces X and forces Y and plug in. Okay, now, one thing to notice is that this came out as a positive value, all right, when I solved this equation mathematically, which means that what I drew in the picture is correct. All right, so I take the signed value and I throw it back into the equation because you wrote these equations to this picture. If you had done that and found RA to be opposite as a negative value, this equation is still valid. I just have to put the negative value in here. Okay, and it will self-correct itself. So draw the free body diagram as you think it is, write the equations, and then don't ever change them. And just use the sign of the value to correct the equations for you. Okay, and then you can, because if I go through and decide, oh, well, I did something backwards and I fixed the diagram, then I got to come in and I got to fix all the equations. And the more times I redo stuff, the more times the chance there are that you make a mistake somewhere along the way. Okay, all right. So then we can come back in and we can do all these others. Again, just plugging in, I can find out that BX is positive to the right and that BY is positive upwards. Okay. Now, again, we can, to check, we can apply a different equilibrium equation. So maybe I decide to sum moments at C just as kind of an exercise. Remember, moments are free vectors. I can sum moments anywhere, and I should get the same result, or I should get equilibrium regardless of where I choose to sum it if we do it. So if I come through and I choose to sum moments at C, see if I can get both of those on there. Can't quite. Maybe if I can pull out just a little bit. Nope. Pull it. There we go. Let's try that. Okay, so now you can see both of the parts. So in this case, just to check for a good exercise, I went and I summed moments out here at C, which would be at the end of the cantilever. Okay, and so this is the equation. I use my real values. So minus 4/5 times the RA value, 4.62. Okay, again, that was a positive value, so it went in as a positive. And now from C, this guy is at 25 feet. It's 10 plus 10 plus 5. Okay, and then plus 12 times sine 60, which is the vertical component again of this guy. And he's at 15. It's 5 plus 10 gets me that. And then minus 12.7, which is my BY value, times 5. Okay, and if I do that, this all mathematically adds up to be minus 0.01 kip feet, which is close enough to 0. It's some round off error probably in this number that caused me some problems. But you're basically 0, it checks, and so that's a way to check those. Okay, all right, good. All right, so let's go try another one. Okay, something a little bit more complex. Get that out of the way. Okay. So now we've got kind of the start of a frame. Maybe it has a snow load on the roof of it. Okay, and so we want to find, in this case, so this could be a structure. It's actually a fairly simple structure. It's just a free cantilever with a leg on it to catch a vertical triangular load, and then we have a distributed load here, and we want to find the reactions at A. And again, this exercise is more about, well, how do you handle the distributed loads? Okay, if you remember, distributed loads are basically loads that are spread out over areas, so we got to find the resultant of that load and then apply it at its resultant location. Okay, and so this is kind of how we go back and do all of this. Okay, so we have 5 kilonewtons on the high end, I have 2 kilonewtons on the low end, and then I have another 2 kilonewton meter acting laterally. Okay, so this guy we know is a rectangular load. We know that his resultant will be acting in the middle. Okay, so if the beam is 15 meters high and it's got a 9 meter leg on it, the resultant load of this is 2 times 15 or 30 kilonewton meters. So if I write the forces in the x equation, that's what I'm doing here. So sum of forces in the x equals 0. I have, again, I'm putting my right hand rule for the fixed support condition, ax to the right, ay up, ma counterclockwise. So I'm going to sum to the right positive, so it's ax plus 2 times the 15. Gives me, tells me then that this is going to be equal to, tells me that my AX then is going to be a minus 30 kilonewtons. Okay, as a result of that, this should be an equal 0, and then that's what's the value of AX is happening on this. Okay, and that should make sense, right? Because all my load is pushing this structure to the right. We're going this way with the load. Okay, so the whole structure wants to move this way. Well, that reaction, which is a resistance to motion, is holding the structure back. So it has to be pushing to the left to hold it. So that's how I get my 30 kilonewtons. The y direction is a little bit more complex, right? Because now I've got this trapezoidal load here, and the way that we handle trapezoids is you could choose to find the resultant of the trapezoid load at its combined trapezoid, but I prefer just to split it into the shapes that I know. So I can split this into a rectangular region in which the resultant is acting at L over 2. And then I have a triangular region, which has a height of 1 kilonewton meter, okay, over that length, which is acting at 2/3 of the distance from the low end or 1/3 from the high. Okay, and that's the way that I would do it. All those together give me the same behavior as a trapezoid. Right, so if I come through and I do this, my force is y equals 0. I'm going to take ay up, positive. I got minus 2 times 9. That's the area of this distributed load, so that's the first term. Okay, and then I get 1/2 of what would be 3 kilonewtons high, because it was 5 high total. See, right there is a 5, and if the trapezoid is 2, then that means the triangular portion is 3 tall. Okay, so 1/2 of 3, and then times 9, its width equals 0. I can solve for AY as being 31.5 kilonewtons acting up as we look at that. Okay, and then to get the moment, same basic idea is that now we come and we get our lengths. So I have... So for this one, it's 2 times 15, and then it's acting at the middle. So if I sum moments at A, and I do that because one of the reasons I like to do that is it gets rid of AX and AY in case I made a mistake here. Okay, if I screwed this up and I sum moments here, I can still get the moment right because I knocked them out of the equation. So that's why I sum moments at A. So 2 times 15 times its centroid of 15 over 2 because it's at a distance of half the height. It gets me that value, and it's going, again, clockwise, so it's a negative. And then I do the vertical uniform load. So it's 2 times, again, we're 9 there, 2 times 9. And then from this line here, that's 9 over 2. And relative to this point, that part wants to go clockwise. So it's also negative. And then I get the triangle portion, which is 1/2 of 3 times 9. which is like we did before, and now it's 2/3 of 9 because it's acting over here somewhere. Okay, and so 2/3 of this dimension gets me the 9. All that equals 0. I can solve for the moment. And in this case, we find out that the moment ends up being a positive, the value. Now, I did include the moment, and the way that I drew it was positive. So this guy went in as a positive, and his math went in as a positive. So that told me that my direction that I drew the picture was absolutely correct. And so that's the 387. And again, you could test somewhere else, and I'll leave that as an exercise for you. Okay, all right, good. All right. Now we can look at a multi-span statically determinate structure on this. Okay, this one actually has internal hinges. Okay, and remember this kind of classifies in as a frame and machine type problem, and anytime you have internal hinges, we always separate them apart. Okay, the free body diagram that we draw, so what we have is I have multi-spans, so A, B, C, D, E, F. The hinges are at B and E. All right, and from A to C, I have 5 kilonewtons per meter, and from C to F, I have 3 kilonewtons per meter. Okay, and it's 20, 20, 50, and 20 are my dimensions for this. And so we draw our free body diagram. Okay, we want to find the reactions A, C, and D, and F. And again, this is what we call statically indeterminate. And we'll talk about determinacy here in a later video to this. But right now I have 5 unknowns on this system and only 3 equations to work with. So we've got to come up with an approach that will allow us to solve this. All right, so if we look at this, first thing I do is I draw a free body diagram of the entire system. Now, if I don't cut the hinges do nothing. Okay, and so all I do is I draw my support reactions. We go through our Y's again. And so my external loads are a 5 kilonewton force from A to C, a 3 kilonewton per meter distributed load from C to F. I have a pin support at AX and AY. I have a roller at CY, a roller at DY, and a roller at FY. Okay, now, right off the bat, I could do a sum of forces in the X. Once I have that first free body diagram, I always write my equations to this guy and see if I can find anything. And it turns out that forces X gets me AX is equal to 0. The others become very complex and don't necessarily give me a lot of information, so we'll hold off on those 2 for now. Okay, but instead we'll use the approach for how do we solve systems with hinges. And if you remember, all you do is you separate based off of the hinges, our basic effects on this. Okay, so if we look at the section from A to B, all I did was you treat a hinge as a pin. Okay, so I have an AX and an AY, and then I have a BX and a BY, and technically this is statically indeterminate too, but from the first picture we found out this guy was 0. All right, so that goes away, and if AX is 0, then that tells me that BX is 0 when I do AX plus BX. Okay, we have our 5 kilonewton meter force happening there, and so now I can do my equations in the Y direction just like we did on the last example, AY plus BY minus 5 times 20, so that's that equation. And then to find either BY or AY, we can sum moments. I chose to sum moments on section AB at B, so that's what this nomenclature is. I'm summing moments at B on member AB, because again, we've blown this thing apart into pieces. This is a valid piece because we've accounted for the internal stuff. So BX and BY are internal forces on that hinge that we have to include as well. And so I chose to sum moments here just to knock those 2 out. Okay, so the only thing I have then is a sum of moments, so it's 5 times 20, that's at the centroid, so that's 20 over 2. Okay, and it's wanting to go counterclockwise, which is positive, and then I do AY times 20 going clockwise, which is a negative, equal to 0. That gets me that AY is 50 kilonewtons. Okay, it's a positive, so it's in the direction of what I assumed. Okay, and again, I always write these with the absolute arrow so that I know what the direction is. Okay. And then once you have the positive 50, I can plug positive 50 here and solve this and find out that BY is also positive 30 on this. All right, now, so that gets us the start of it. Now, the key to solving these hinge problems is you got to find the hinge forces. Okay, and so if we look, now what I did is I went over and I did the other side of this thing kind of in a similar fashion. I jumped over to E. Okay, so EX, EY, and FY. So now I'm looking at the piece that is from here to here, okay, and its load is 3 kilonewtons per meter. And again, I did Y's on all of these, weight, internal supports, external on those. It's the load is a little different, and the length is, now 20. Okay, and so then sum of the forces in the X equals 0 tells me EX is 0 because there's nothing on it, so that makes sense. Sum of forces in the Y is EY plus FY minus 3 times 20. Gets me that equal to 0. Again, I can't solve it. I have 2 unknowns, so I'm forced to go back to the moment equation. This time I sum moments here at E at the hinge, because that's where I had the most unknowns. and I assume counterclockwise positive is my direction, so the 3 kilonewtons is going to be 3 times 20 over 2, and that guy wants to go in a clockwise direction around that point, so that's why he goes in as a negative. And then the Fy is Fy times 20, and it wants to go counterclockwise, that's why it was a positive. All right, and with that, now Fy is 30 kilonewtons acting up, and then I can do Ey as a result coming back out of this equation. When I take 30 into here, this guy is also 30 acting up. So that gets me those two pieces. Okay, once I have that, then I can go get the guys in the middle. Okay, and the trick here is that basically, remember, internal forces on one picture are opposite on the other. So even though I didn't draw it, this guy would draw in as Ex equal to 0 there, and my Ax would be, or sorry, my Bx would be Bx equals 0 here. Okay, if I put them on the picture to include them, that's good. And then I have By from before, and I have Ey from before, and then all I have left is to find Cy. All right, sorry about that. Once we have our free body diagram established, then we can go back and we can write our equation. And I saw a typo, I guess if you will, on here. Okay, so all I'm going to do is I'm going to sum moments at D at this location on this free body diagram. Notice that I've got the hinge force By and the hinge force Ey. There's more than one way to do this, and that was part of where I kind of mixed methods and kind of got tangled up for a second, but it's all resolved now. All right, so if I take this as my D, then my support reaction from the hinge, or sorry, my hinge reaction from By was 30 kilonewtons acting up on the picture that was up at the top. So now it's 30 kilonewtons acting down. So then the moment that this causes about D is a positive 30 times 20 plus 50, or 30 times 70. So it's wanting to go this way around D. Okay, so that's why it's a positive. Okay, and then I have the distributed load, which has a magnitude of 5 times 20, because it's 5 high and 20 wide, and its centroid is here in the middle, and that's now 10, half of 20, plus 50, or 60 from my D, and it's wanting to go counterclockwise also. So if I slide this down just a little bit, try to get the glare out. Okay, my Cy is unknown, okay, that's times 50, and it's going clockwise, so negative. And then this distributed load is kind of odd, that the whole magnitude is 3 times 50 plus 20, or 70, okay, and then its centroid is at 35 from one end, so it's 15 to the left of D. That's why we have a 15 here, okay, and since it's to the left of D, it's causing it to go counterclockwise again, so that's why it's a positive. And then I get my Ey reaction, which again was 30 kilonewtons acting up here, has to be 30 kilonewtons acting down here. And so 30 times a distance of, that should be a 20. Okay, and that will get us our math there. And so, yes, let me correct that real quick. All right. So with that little correction made, my number then is 213 kilonewtons acting up. And then I can do sum of forces Y on this guy. So it's a minus By minus 30 minus 5 times 20, which is the distributed load, plus the Cy I just got, 213, okay, acting up. And then I have the 3 for 70, minus 3 times 70, plus the dy, and then minus the 30, okay, which is this minus sign right there. Okay, and if I do all of that math, then I find out that dy is 157 kilonewtons acting up. Okay, and these numbers make sense. And the problem I was having before and why I kept stuttering is that I did the calculations and my dy had ended up larger than my Cy. And I knew that was wrong because if I look at the structure, and this is where engineering judgment kind of comes in, you're always doing this and trying to think about, what are the numbers telling you? That this structure was symmetrical, but most of the load was on the left or to the left of Cy. So the majority of the load, or a larger portion of the load, should go to Cy. All right, so Cy had to be bigger than dy, and it wasn't when I did my calculations, so I knew something was wrong. And so in this case, then I was able to fix it, and indeed, the calculations now confirm that dy is a little bit less than Cy because of the extra distributed load happening there. So anyway, that's kind of our internal hinge problem. The methodology is sound. It's just getting through the math and making sure that you get your dimensions. And I was pretty sloppy about how I did stuff, and so I guess that was a good example of how not to do it. But at the end of the day, make your free body diagrams clear and concise, put the dimensions on them, and then just make sure that you write the equations true to the picture that you did. And that was the problem, is I hadn't done that here. And so hopefully that makes a little bit more sense. I apologize for any confusion that may have caused. Okay, all right. All right, so that kind of concludes kind of our basic statics review of simple forces, simple moments on a couple of different types of structures. I hope it's kind of helped knock some of the dust off. I apologize for some of the rough spots in the middle there, but like I say, just a little bit of engineering judgment will go a long way, and we'll always try to help bail you out. So, as always, if you have any questions or comments, please let me know. Leave me some comments down below, and I'll be happy to try to address that. And then I promise that they'll be a little bit better going forward. So I apologize for any difficulties that this one caused. So hope it makes sense. Wish you all a wonderful afternoon and happy engineering. Thanks. Bye.